The next series of examples involve unsymmetrical curves. Learn how this example is solved here in engineering surveys. There are two curves which connect a back tangent of positive 5% with a forward tangent of negative 8%. The curve after PVC is 40 meters, connected to the next curve of 60 meters. Other details are for PVC, with elevation of 110 meters and station of 6 plus 780. There is also an outcrop located at station 6 plus 800, with an elevation of 108.4 meters. The first requirement is to determine the height of fill to cover the outcrop. The next is to look for the elevation of the curve at station 6 plus 820. Lastly, the elevation and station of the highest point are also required. Illustrate the unsymmetrical curve again, starting with the back and forward tangents of positive 5 and negative 8%. There is a different curve from PVC to PVI, and another curve from PVI to PVT. The other details are for PVC. Those are elevation of 110 meters and station of 6 plus 780. The first curve has a length of 40 meters, and the second has 60 meters. Apart from this data, there is also an outcrop at station 6 plus 800, with an elevation of 108.4 meters. First is to look for the height of the fill for the outcrop. Checking on the location of the outcrop, it is exactly at the midpoint of the first curve, which means that we can use the function of h from symmetrical curves. To solve for the height of the fill, we need to take the elevation of the point on the curve, and that is by having h1. This is the gap between the tangent to the curve. Treating the first as a symmetrical curve, h is taken from the function of 1/8 of L1 times the difference of the gradients. The gradients for the curve are g1 and g3. So we can take h1 as 1/8 of 40 times 0.05 less g3, which can be simplified as 5 of 0.05 minus g3. The problem is, we don't know g3. Nonetheless, from the derivation of functions in unsymmetrical curves, g3 was derived as g1 less twice of h over the length of the first curve. Plug in figures and have 0.05 less 2h over 40, or this is 0.05 minus 0.05h. Substitute this into h1 and get 5 of 0.05 minus g3, which is 0.05 less 0.05h. Cancel out 0.05 and get h1 as 5 of 0.05h, which makes 0.25h. All we had cleared out right now is h1 in terms of h. So check on other functions to help get h. From the equation involving the length of the curve, in identifying PVI, there is L1 as equated to 2h L2 upon L2 with a difference of grades minus 2h. L1 is already given as 40, so there is 40 as equal to 2h times 60 divided by 60 of 0.05 minus negative 0.08. Then subtract 2h. The function is simplified as 40 as equal to 120h upon 7.8 minus 2h. Cross multiply to have 312 minus 80h as equated to 120h. Take all with h and have 200h is equal to 312, where h is 1.56 meters. Finally, for h1, from 0.25 of h, that is 0.25 of 1.56, making h1 0.39 meters. The next parameter to consider is the elevation of the tangent at station 6 plus 800. This is solved by using the gradient and PVC, giving height as 0.05 of 20 meters. 20 meters is L1 over 2, as we are referring the computation from PVC. The height turns out as 1 meter. Starting from the point with known elevation, PVC, of elevation 110 meters, raise this height by 1 meter to reach the tangent elevation of station 6 plus 800. The tangent height is then 111 meters. Next is to subtract h1 of 0.39 meters to determine the curve height. The height of the curve station at 6 plus 800 is then 110.61 meters. Subtract from there the outcrop elevation of 108.4, giving the thickness of the fill as 2.21 meters. Next is the elevation of the curve at station 6 plus 820. This station is aligned to PVI, and the elevation is solved by using h, which was previously computed. What is required for now is the elevation of PVI, which is solved using gradient. The height of PVI compared to PVC is computed as 0.05 times 40 meters, which turns out as 2 meters. Thus, from the elevation of PVC, which is 110 meters, add the height of 2 meters to reach the elevation of PVI, which is 112 meters. From this elevation, subtract h of 1.56 to have the elevation of the curve at station 6 plus 820, which is 110.44 meters. The last requirement is the elevation and stationing of the highest point of the curve. The highest point of this unsymmetrical curve is located on the first, so the distance of this point to PVC can be solved from S1, which is equal to G1 with the square of L1 upon 2h. This is then 0.05 times the square of 40, all over twice of 1.56, giving 25.64 meters. The stationing is then referred from PVC with station 6 plus 780. Add S1 of 25.64, and the station of the highest point is at 6 plus 805.64. For the elevation, use the function for vertical offsets, that is the ratio of x squared with the y as equal to the square of the length of the first curve upon h. By plugging the known values, the function becomes the square of 25.64 is to y, and this is equal to the square of 40 over 1.56. Y is then 0.64 meters. This y value is the distance between the tangent and the curve, so we still need to know the elevation of the tangent. The tangent elevation is computed from gradient, that is 0.05 of the distance 25.64, giving 1.282 meters. With the known height, take the elevation of PVC, which is 110 meters. Then add the tangent height of the highest point station, which is 1.282. The total is then the elevation of the tangent, which is 111.282 meters. Subtract from here y of 0.64, so the elevation of the highest point is 110.642 meters.